you ever wondered what happens to a star when it dies? Some stars end their lives in a spectacular explosion, leaving behind a core that is so dense and fast that it defies our common sense. These are pulsars, one of the most fascinating and extreme objects in the cosmos. Today, we will explore what pulsars are, how they work, and why they are important. Thank you for watching, and enjoy. Pulsars are rapidly rotating neutron stars that emit pulses of radiation at regular intervals, ranging from milliseconds to seconds. They are the ultra-dense leftover cores of massive stars that exploded as supernovae. But how do they form? Let's go back to the moment when a star dies. A star is a giant ball of plasma that is held together by gravity and powered by nuclear fusion. Fusion is the process of combining lighter elements into heavier ones, releasing energy in the process. For most of their lives, stars fuse hydrogen into helium in their cores. This energy balances the inward pull of gravity and keeps the star stable. However, as the star runs out of hydrogen, it starts to fuse helium into carbon, and then carbon into oxygen, and so on, until it reaches iron. Iron is the most stable element and cannot be fused into anything else. This means that the star has exhausted its fuel and can no longer produce enough energy to support its own weight. Gravity wins, and the star collapses. The collapse happens so fast that it triggers a massive shockwave that rips apart the outer layers of the star in a brilliant explosion called a supernova. This is one of the most powerful events in the universe, and it can be seen from billions of light years away. A supernova can even outshine an entire galaxy for a brief moment. But what happens to the core of the star after such an event? Well, that depends on how massive the star was. If the star had a mass between 8 and 20 times that of the Sun, the core can collapse into a neutron star. A neutron star is a ball of extremely dense matter that is composed almost entirely of neutrons. Neutrons are subatomic particles that have no electric charge and are slightly heavier than protons. A neutron star is so dense that a teaspoon of its material would weigh about 1 billion tons on Earth. A neutron star is also very small, with a diameter of only 20 kilometers, or 12 miles. That's like squeezing the mass of 1 million Earths into a ball the size of a small city. A neutron star is also very hot, with a surface temperature of about 1 million degrees Celsius, or 1.8 million degrees Fahrenheit. But how does a neutron star become a pulsar? The answer lies in its rotation and magnetic field. When the star collapses, it conserves its angular momentum, which is the measure of how fast something spins. This means that the smaller the star becomes, the faster it spins. Imagine a figure skater pulling in their arms to spin faster. This is called the conservation of angular momentum. A neutron star can spin up to 700 times per second. That's faster than the blades of a helicopter. As the star spins, it also generates a very strong magnetic field, which is a force that can attract or repel other magnets or electric currents. The magnetic field of a neutron star can be 1 trillion times stronger than that of the Earth. The magnetic field of a neutron star has 2 poles, just like a bar magnet. However, the poles of the magnetic field are not aligned with the axis of rotation of the neutron star. This means that as the neutron star spins, the magnetic poles also move around. This creates a lighthouse effect, where the magnetic poles emit beams of electromagnetic radiation, such as radio waves, X-rays, or gamma rays. The electromagnetic radiation is produced by the acceleration of charged particles, such as electrons and protons, along the magnetic field lines. The particles are accelerated to near the speed of light, which is the fastest speed possible in the universe. The particles also emit light as they spiral around the magnetic field lines. The beams of electromagnetic radiation are very narrow and focused, like the beams of a flashlight. They can only be seen when they point toward the Earth, just like a lighthouse can only be seen when it points toward a ship. This is why we see pulsars as regular, repeating pulses of light. The time between the pulses is the same as the time it takes for the neutron star to complete one rotation. This is called the period of the pulsar. Pulsars are very precise in their periods. They can be measured to a fraction of a nanosecond, which is a billionth of a second. In fact, some pulsars are more accurate than the best atomic clocks on Earth. That's why astronomers use them as natural timekeepers and navigational tools in space. For example, the Voyager 1 spacecraft, which is now the farthest human-made object from Earth, carries a map of 14 pulsars with their periods and directions as a way of telling any potential alien civilization where we are in the galaxy. Pulsars are not only useful, but also beautiful. They are surrounded by stunning nebulae, which are clouds of gas and dust that glow with different colors. Some of these nebulae are shaped by the pulsar's powerful wind, which is a stream of charged particles that flows out from its surface at nearly the speed of light. This wind interacts with the surrounding magnetic field and creates complex structures, such as jets, arcs, and rings. One of the most famous examples of a pulsar wind nebula is the Crab Nebula, which is the remnant of a supernova that was observed by Chinese astronomers in 1054. At the heart of the Crab Nebula lies a pulsar that spins 30 times per second and emits pulses of radio, optical, X-ray, and gamma-ray radiation. Pulsars are truly cosmic wonders that reveal the extreme physics and beauty of the universe. They are the ultimate laboratories for testing scientists' theories of gravity, matter, and energy. They are also the source of some of the most energetic and mysterious phenomena in the cosmos, such as fast radio bursts, gamma-ray bursts, and gravitational waves. Pulsars challenge our imagination and inspire our curiosity. They are the beacons that guide us through the dark and vast ocean of space. Thank you for joining me on this journey. I hope you enjoyed it and learned something new about these incredible objects. If you did, feel free to show your support with a thumbs up or by sharing this video with someone else who may enjoy it. I would also love to hear your thoughts on this video in the comments. If you would like to see more videos like this in the future, feel free to subscribe. Thanks again. Until next time, take care and be well.